Picture this. It's late. The only light in the garage comes from a single bare bulb hanging overhead. The air smells of solder, old plastic, and that faint electric tang of ozone. All around you are shelves overflowing with components, bins of resistors, and forgotten projects. In the center of it all, humming softly, is a machine that shouldn't exist. It's a sprawling contraption of wires, custom-etched circuit boards, and dozens of vintage microchips, each one a tiny monument to a bygone era of computing. This isn't just another retro computing project. This is an attempt to do something, well, something a little bit crazy. We're going to try and touch the ghost of quantum mechanics with hardware from the 1980s. We're building a quantum simulator in my garage. This whole idea started, as many of my projects do, with a question, a what if that I just couldn't shake. What if we could take the building blocks of the first home computer revolution and use them to explore the most mind-bending concepts of modern physics? It's the ultimate engineering challenge. It's a collision of two worlds, the tangible, predictable logic of 8-bit processors and the probabilistic, weird-as-heck reality of the quantum realm. It's about getting your hands dirty with the fundamental nature of the universe. It's about building something, not because it's practical, but because it feels impossible. This machine is our vessel for that journey. The goal isn't to build a true quantum computer. Let's be clear about that. The big labs with their billion-dollar budgets are working on those. No, our goal is different. It's about simulation. It's about creating a model, a digital echo of a quantum system, so we can poke it, prod it, and maybe, just maybe, wrap our heads around how it works. We're using a classical machine, built from very old parts, to mimic the behavior of a quantum system. It's like building a meticulous scale model of a hurricane inside a snow globe. The process of building the model is where the real learning happens. It forces you to understand every gear, every circuit, every line of code. And that's the real magic of this project. It's a testament to the idea that science and engineering aren't just for people in white lab coats. They belong to the curious, the tinkerers, the builders. This machine, with its blinking LEDs and tangled wires, is a physical manifestation of that curiosity. It's a beautiful, over-engineered, and slightly absurd monument to the joy of making. It's a bridge built from silicon and solder, connecting the dawn of personal computing to the frontiers of physics, and we're about to flip the switch. So, what is this quantum ghost we're chasing? It's a phenomenon called quantum entanglement. Albert Einstein famously called it spooky action at a distance, and honestly, that's one of the best descriptions I've ever heard. Imagine you have two particles, let's call them particle A and particle B. They are created in a special way so that they become linked. Their fates are intertwined. Now you can separate these two particles. You can send one to the other side of the room, or the other side of the galaxy. The moment you measure a property of particle A, say, its spin, you instantly know the spin of particle B. Instantly. Faster than the speed of light. That's the part that baffled Einstein and continues to baffle us today. How do they communicate? The truth is, they don't. They aren't sending signals. They are, in a very real sense, still part of a single system, no matter how far apart they are. Measuring one is like measuring the whole system. This interconnectedness is the heart of entanglement. It's not just a weird theoretical idea, it's a cornerstone of quantum mechanics and the key to building powerful quantum computers. It's a property of our universe that feels like it breaks the rules of our everyday experience, because, well, it does. Simulating this spooky action is incredibly difficult for a regular computer. The problem is complexity. A single quantum bit, or qubit, can be a 0, a 1, or both at the same time, a superposition. That's already weird, but when you entangle two qubits, you can't describe them individually anymore. You have to describe the entire 2-qubit system at once. For 2 qubits, you need 4 numbers to describe their state. For 3 qubits, you need 8. For 4, you need 16. The number of variables you need to track doubles with every single qubit you add. This is called exponential scaling. This is why your laptop, powerful as it is, would grind to a halt trying to simulate even a modest number of entangled qubits, maybe 50 or 60 of them. The amount of memory required becomes larger than all the memory in all the computers on Earth combined. You're trying to describe a system that holds an immense amount of information. To truly model entanglement, you need a different kind of computational muscle. Or, in our case, a very strange, very specific kind of parallel architecture built from parts that were never, ever designed for this kind of work. That's where the real challenge, and the fun, begins. When you decide to build a massively parallel computer in your garage to simulate quantum physics, you have a lot of choices for the brain of the operation. You could use modern microcontrollers, FPGAs, or any number of powerful, efficient chips. So why on earth did we choose the MOS Technology 6510? For me, the answer is simple: the Commodore 64. That computer, powered by the 6510, was a gateway for millions of people. It was the machine that taught a generation to code, to tinker, and to dream. It was simple, it was elegant, and it was approachable. The 6510 isn't just a processor, it's a piece of history. It has character. The 6510 is an 8-bit processor. That means it works with data in chunks of 8 bits at a time. It has a simple instruction set and a clock speed of around 1 megahertz. That's 1 million cycles per second. Your smartphone is probably doing billions of cycles per second. So we're talking about a massive difference in raw speed. But speed isn't everything. The beauty of the 6510 is its simplicity. It's a chip you can understand completely. You can read the data sheet, learn its assembly language, and know exactly what it's doing on every single clock cycle. This transparency is crucial when you're trying to build a complex, custom system from the ground up. The challenge, of course, is monumental. We're asking an 8-bit chip design to run games like Jumpman and Pac-Man to handle the complex mathematics of quantum state vectors. It's like asking a donkey to do the job of a racehorse. A single 6510 couldn't even begin to handle the task. It would be comically slow. But what if we didn't use just one? What if we used dozens of them, all working together? That's the core idea of our array. We're trading the raw speed of a modern CPU for the massive parallelism of a whole army of old, slow ones. This choice also forces a certain kind of creativity. We can't just throw a standard algorithm at this thing. We have to adapt. We have to be clever. We have to break down the enormous problem of quantum simulation into tiny, 8-bit sized pieces that each processor can handle. It's a puzzle. How do you map the abstract, continuous nature of a qubit superposition onto the discrete, chunky world of 8-bit integers? How do you coordinate dozens of these processors so they act as a single, coherent machine? The limitations of the hardware become the guideposts for innovation. It's in solving those problems that the real engineering magic happens. So, how do you get 64 of these classic chips to work together? You can't just wire them up and hope for the best. You need an architecture. Our design, which we affectionately call the Q6510 array, is a grid of processors. We settled on an 8x8 grid, giving us a total of 64 nodes. Each node is its own tiny computer, a 6510 processor, a small amount of RAM, just 2 kilobytes per node, and a custom I/O chip to handle communication. The whole thing is laid out on a series of custom-designed printed circuit boards, or PCBs. I spent weeks designing these boards, routing every single trace, making sure every connection was perfect. It was a labor of love. The key to making this array work is communication. A bunch of isolated computers isn't a parallel machine, it's just a pile of computers. We needed a way for the nodes to talk to each other, and to talk to a central controller. For this, we designed a custom communication bus. Each node can send data to its immediate neighbors, up, down, left, and right. This mesh network topology is great for problems where data needs to be shared locally, which is perfect for some of the quantum simulation algorithms we have in mind. A master controller, based on a more modern microcontroller, is responsible for loading the programs onto all 64 nodes and collecting the final results. Now for the fun part, representing a qubit. A qubit state is described by two complex numbers. A complex number has a real part and an imaginary part. So, to describe one qubit, we need 4 numbers. The 6510 can only work with 8-bit integers, which go from 0 to 255. So we use a technique called fixed-point arithmetic. We basically pretend that those 8-bit integers are fractions. We allocate 2 bytes, 16 bits, for the real part and 2 bytes for the imaginary part of each complex number. This means a single node with its limited RAM can hold the state of just 1 or 2 simulated qubits. The whole array works together to hold the state of the larger entangled system. The physical build was an epic saga in itself. Sourcing 64 working 6510 chips from 2025 was a challenge. Many were pulled from non-functional Commodore 64s. Then came the soldering. Thousands upon thousands of solder joints, each one done by hand. We had to build a custom power supply system to feed the beast. These old chips are thirsty. The final machine is a beautiful monster. It sits on a custom-built rack, a web of ribbon cables connecting the boards. It's a physical data structure, where the architecture of the machine reflects the problem it's trying to solve. It's a piece of functional sculpture. The moment you first apply power to a project this big is always pretty terrifying. You flip a switch, hold your breath, and just hope you don't see the magic smoke that signals a fried component. Our first power on was, well, eventful. A few LEDs blinked, a capacitor on one board popped with a sad little fizz, and then silence. But you know, that's not failure, that's just the first data point. We troubleshooted, found a reverse capacitor, classic mistake, replaced it and tried again. This time, success. All 64 nodes lit up their heartbeat LEDs, a steady rhythmic pulse that told us the processors were alive and running their initial test loops. It was honestly a beautiful sight. The first real program we ran was a system diagnostic. We needed to know if every node could run code, and crucially, if every node could talk to its neighbors. The master controller sent a simple instruction. Node 0, generate a number and pass it to your right. Every other node, listen to your left. Add 1 to the number you receive, and pass it to your right. The results would then ripple across the grid, from left to right, row by row. We hooked up a display to the master controller to watch the data come in. We saw 0, then 1, then 2, all the way up to 63. It worked, the data was flowing. To visualize this flow, we wrote a more advanced diagnostic. This time, we had the master controller assign a color value to each node based on its position in the grid. Then, we ran a simple pass the pixel program. Each node would send its color value to its neighbor in a rotating pattern. On a monitor, connected to the system, we saw beautiful, flowing patterns of color washing across the 8x8 grid. It looked like a low-resolution screensaver from the 90s, but to us, it was proof. It was confirmation that our home-built parallel computer was not just a collection of parts but a single, cohesive system. This visualization was more than just a cool light show. It was an essential debugging tool. When one node failed to communicate, we'd see a black dead pixel in our pattern. If data got corrupted, the colors would be wrong. We could literally see the flow of data and pinpoint problems in the hardware or the low-level communication code. This kind of visual feedback is honestly one of my favorite parts of building physical things. You're not just staring at a debugger on a screen, you're interacting with the machine on a physical level. You can see the logic happening in front of you, one blinking light at a time. Alright, the machine works. Now for the main event, simulating entanglement. The core of any quantum simulation is matrix multiplication. A quantum operation, like measuring a qubit or entangling two of them, can be represented as a mathematical object called a matrix. To simulate that operation, you multiply the current state of your qubits, which is a list of numbers called a state vector, by that matrix. This gives you the new state of the qubits. It's, a lot of number crunching. And for our little 8-bit processors, it's a very heavy lift. We can't just use a standard library. We have to write it all from scratch in 6510 assembly language. Let's use an analogy. Imagine our state vector is a list of ingredients for a recipe. An operation like a C0 gate, which is a fundamental entanglement gate, is like a set of instructions. Take half of the flour and mix it with all of the sugar. Take the remaining flour and mix it with the eggs. Our processors have to perform these instructions. But since our recipe, or state vector, is spread out across all 64 nodes, they have to coordinate. One node might be in charge of the flour, another the sugar. They have to pass numbers back and forth to complete the calculation. It's a highly choreographed digital dance. Here's a simplified look at what the code does. We're not writing C++, we're writing in something that looks more like this: assembly. For example, simplified code for one node LDA node awk memory. A. Load a number from this node's memory, STA, temp, storage. Store it temporarily. JSR, send right. Call subroutine to send it to the right neighbor. JSR, receive, just left. Call subroutine to wait for a number from the left add temp storage. Add the received number to our original number, sta node. Memory, B. Store the new result. This is just a tiny fragment of the thousands of lines of assembly code required. Each line is a simple, direct command to the processor. Load a byte, add a byte, store a byte. We had to write our own custom routines for 16-bit addition, subtraction, and multiplication, because the 6510 can only handle 8 bits at a time. It's painstaking work, but it gives us complete control. The most challenging part was implementing the multiplication of complex numbers. Remember, each number has a real and imaginary part. The formula for multiplying two complex numbers is a bit messy. It requires 4 separate multiplications and 2 additions or subtractions. For our 6510s, this is a long sequence of operations. We optimized this code for weeks, shaving off every possible clock cycle, trying to make it as efficient as possible. The final algorithm is a ballet of data shuffling, where partial results are passed between nodes combined and stored, until the entire matrix multiplication is complete and the new quantum state is calculated across the whole array. After all the building, coding, and debugging, it was time to simulate the spooky action. We decided to simulate a simple 2-qubit system. This doesn't push the array to its limits, but it's the hello world of quantum computing. We start by initializing the 2 simulated qubits into a simple state. Let's say both are ket 0. In our array, this means setting the first number in our state vector to 1 and all the other numbers to 0. This initial state is distributed across the nodes. On our visualizer, this looks like a single bright pixel in the top left corner of the grid. Next, we apply the first quantum gate, a Hadamard gate on the first qubit. This puts the qubit into a superposition, a 50-50 state of being both 0 and 1 at the same time. We send the command from the master controller, and the array gets to work. The nodes perform their matrix multiplication ballet. A few seconds later, seconds, the calculation is done. The new state is calculated. Now, our visualizer shows 2 bright pixels of equal intensity. This represents the equal probability of the first qubit being 0 or 1. The system is working as expected. So far, so good. Now, for the magic. We apply the controlled NOT, or CNOT, gate. This is the gate that creates entanglement. It connects our 2 qubits. It says, if the first qubit is 1, then flip the second qubit from 0 to 1. Because our first qubit is in a superposition of both 0 and 1, the outcome is weird. The array chugs away again, passing numbers, performing its 8-bit arithmetic. The final state is calculated. On the visualizer, we now see 2 bright pixels again, but in different positions. They represent the 2 possible outcomes for the system. Either both qubits are 0, or both qubits are 1. The states where one is 0 and the other is 1 have disappeared. They have 0 probability. This is it. This is entanglement. The fates of our 2 simulated qubits are now linked. Before we measure, the system is in a superposition of ket 00 and ket 11. Now, we perform the measurement. This is simulated by having the array randomly pick one of the possible outcomes based on their probabilities. Let's say it picks ket 11. This means we measured the first qubit and found it to be 1. Because of the entanglement, we know, instantly, and without measuring it, that the second qubit is also 1. We run the simulation again. This time, it might collapse to ket 00. We measure the first qubit as 0, and we know the second is also 0. We never, ever get a result of ket 01 or ket 10. The correlation is perfect. The spooky action is in our machine. Building and running this machine has been an incredible journey, but it has not been without its challenges. This is not a modern, reliable computer. It's a temperamental beast built from 40-year-old components. Reliability is a constant battle. A single 6510 chip might have a tiny flaw that only shows up under specific conditions. A solder joint can crack. A ribbon cable can come loose. Finding a single faulty node in a 64-node array can be a nightmare. Our diagnostic visualizations have been our best friend, allowing us to spot dead or misbehaving nodes at a glance. Then, there's the noise. I'm not talking about audible noise, though the fans do make a bit of a hum. I'm talking about electrical noise. With hundreds of wires carrying signals back and forth, you get crosstalk. A signal on one wire can induce a small current in a neighboring wire, potentially flipping a bit from a 0 to a 1. We had to be extremely careful with our board layout and use shielded cables where possible to minimize this. Even so, we occasionally get random bit flips. In the context of a quantum simulation, this looks like a small error in the final probabilities, a little bit of decoherence introduced by the hardware itself. The limitations are also very real. The precision of our calculations is limited by our 16-bit fixed point numbers. We can't represent the quantum states with perfect accuracy. This introduces small rounding errors that can add up over time, especially in more complex simulations. And then there's the speed. While an 8x8 array is impressive, simulating just a 6-qubit system, which has a 64-element state vector, takes several seconds. Simulating 7 qubits would require twice the memory, which we don't have. To simulate more qubits, we would need a much larger array. The exponential scaling problem is a wall we can't easily climb with this architecture. But these limitations are also part of the lesson. They give you a real, tangible appreciation for the difficulty of what we're trying to simulate. When you see a bit flip corrupt your quantum state, you gain a gut-level understanding of the problem of quantum decoherence that real quantum computers face. When you see your simulation slow to a crawl as you add just one more qubit, you truly feel the power of exponential scaling. These aren't just abstract problems in a textbook anymore. They are real, physical hurdles that we have to engineer our way around. The imperfections of the machine teach us as much as its successes. So, what's the takeaway from all this? Did we build a practical quantum computer? Absolutely not. But we succeeded in our real mission, to use the process of building to learn. This project was a deep dive into 2 different worlds at once. It forced us to understand the architecture of an 8-bit computer at the deepest level, while simultaneously forcing us to grapple with the bizarre rules of quantum mechanics. The act of translating the mathematics of quantum states into the primitive language of 6510 assembly code was an education like no other. It's one thing to read about a state vector, it's another thing entirely to build a physical machine that holds one. This experiment reveals something beautiful about the nature of computation itself. It shows that computation is not just about speed, it's about architecture. It's about mapping the structure of a problem onto the structure of a machine. Our array, with its grid of locally connected processors, is a terrible machine for browsing the web, but it's surprisingly well suited for this very specific type of scientific simulation. It's a reminder that there's no single best computer. The best computer is the one that's designed for the job you need it to do. Sometimes, that means a whole army of slow, simple parts is better than one fast, complex one. Looking to the future, this project is just a beginning. The real quantum computers being built in labs today are the true pioneers. They aren't simulating quantum mechanics, they are living it. But simulation still has a vital role to play. It helps us develop algorithms, test theories, and understand the systems we're trying to build. Our little 6510 array is a humble tribute to that spirit of exploration. It's a proof of concept, a demonstration that you can explore the biggest ideas in science with unconventional tools. It's a celebration of the garage inventor, and it leaves me with a final, tantalizing question. If we can simulate quantum entanglement on a pile of Commodore 64 chips, what else is possible? What other impossible feats could we attempt by repurposing old technology in new and creative ways? What scientific mysteries could be unraveled with a machine built from forgotten parts and a whole lot of curiosity? The universe is full of fascinating problems. The world is full of interesting junk. I say we get out there, get our hands dirty, and see what we can build. The only myth worth busting is the one that says you can't.